Hello, everybody. Today we will be talking about logic, the last part of it. This will conclude our logic packet. So this is, follow up of the stuff that we did last time, which was on proving using statement and reason with the logic. So, MP, MT, DS, and also S. So there is an extension beyond that because out of those four rules that we can use for statement and reason, there are actually six more that we can possibly use. Now, we don't really see these six rules that too often, but it is actually good to have it in the background just in case. It's basically like a toolbox utility. So let's go ahead and talk about that then. Okay. So the first thing I want to mention is something called logically equivalent. So as you can see in the statement right here, I am going to kind of point it out right here on the side. The symbol that has kind of like a three dashes, almost like an equal sign or some sort, it's called logically equivalent, which means that the two statements are exactly the same. So I came up with two examples right here where you have something that is actually logically equivalent, meaning that they mean exactly the same thing. The example is, it is not true that, in quotation, I like avocado or I like durian. Then if you read the statement, it is not true that I like avocado and it is not true that I like durian. If you think about it, just reading it out loud in English, plain old English, they definitely sound exactly alike. And we can actually prove that. So this is an example of what is known as logically equivalent. Now, to help you prove this, let's go ahead and do the following. Let me take the first sentence and write it in a statement. So then that way, oops, sorry, kind of dropped it. Let me go ahead and write the first statement in a form. So then that way we can kind of prove it using a truth table. So let's see here. The first one, I can write the following. The negation of let's see, in parentheses, because you can see the quotation mark, I'm going to go ahead and say I like avocado as A. And then we have or, I like durian, so that means it's going to be denoted as D. So that's what that statement is going to say. Now, in the second statement, it's kind of the same idea. Now, this guy right here is going to be, it is not true that I like avocado. So that is the negation of A using the symbol and, then we have the negation of D. So what I would like to do is take these two, right, and prove that they are logically equivalent to each other. So the question is, I need to show, that's what NTS stands for, that the negation of A and D is logically equivalent to negation of A and negation of D. Okay, so we can kind of do like a quick proof down here just to kind of show that, again, using the truth table. So if you remember from, let's see, I think like 2 or 3 sessions back, first what we'll do is we'll go ahead and build the truth table for each one and make sure that they come out to be exactly the same thing. So in the first case, I'm going to go ahead and build D and A, right? And then I'm going to build A or D. And then from that, I am going to build the negation of A or D. Okay, so let's see what we have here. So first, we're going to put in the first one, which is going to be TT, TF, FT, and then finally FF. Okay. In the case of an OR statement, now remember, if it's both true, then that means that the OR statement is true. And in an OR statement, if one of them is false, the whole thing is still true because it could be either or. So this is going to be T, this is going to be T, and the only one that's false is going to be the last one because they're both false. Now, I'm going to take that third column right here and solve for the fourth column by doing the opposite because it wants the negation of A or D in parentheses. So the final result for that one is F, 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 T. Okay. Now, if I do the same thing for A, negation of A and negation of D, I should get the same result, F, 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 T then. If I do, then that means that these two statements are logically equivalent to each other. So let's go ahead and test that out then. So we have A, we have D, okay? Let's see, we want to build negation of A. We want to build negation of D. And then finally, we can take the two together and then look at the AND scenario of the two statements. Once again, I'm going to start out with TT, and then we have TF, and then we have FT, and then we have FF. it is important that the beginning part right here is the same as the beginning part right here, because otherwise you're going to get things mixed up. All right, here we go. Negation of A, so TTFF, so that means we have FFTT. Negation of D, so that's going to be FTFT. And finally, we're going to take the AND scenario of both of them. So in an AND scenario, let's see, both of the statements are going to be false, so that means that the AND scenario will be false. Now remember, for AND, if at least one of them is false, then the whole thing has to be false then, because both statements have to be true. So that means if it's FT, it has to be F. If it's TF, it has to be F. And the only case where it's going to be true is both are equal to T. So that means that there it goes. And hey, look at that. If you look at what we have, FFFT and then FFFT. So therefore, this right here is legitimate. So that means that they are logically equivalent to each other. And we can put a smiley face next to it because, Saitama is okay with it. All right, now let's go ahead and look at these rules that I was referring to. So the one that I just did right here, this is actually one of the rules that I just proved, and that's going to be De Morgan's rule right here. So each one of these are basically going to be theorems that we're going to be using in this case, along with the other 4 theorems that we learned in the previous section. Now, for each one of these theorems, number 5, 7, 9, 8, and 6, and 10, you can prove them each one by using a truth table like I just did previously. I'll go ahead and let you try it out on your own, and hopefully it'll work out. But more importantly, what I like to do now is I want to use these theorems in order to do statement and reason, because that's really what we're going after. Okay, so now we have everything in our arsenal. Let's go ahead and see if we can do a statement and reason with these rules. And this is something that you might want to write on the side because it's very easy to actually kind of forget some of these. Okay, all right, so here we go. Number 4. Now this one I kind of stole from a textbook, number 4, hint. So let's go ahead and see if we can actually prove this one right here. Given we have in quotation P and Q, that is going to imply S. Then we have the negation of S. What I want to do is I want to prove negation of P or negation of Q. Now, again, looking at what we have and what we want, I think I can kind of see something to begin with. Notice that, and let me just go ahead and kind of circle it for you. We have negation of S, and then we have this statement right here. That right there screams out MT, modus tollens, if you remember correctly. And modus tollens, let me just go ahead and write it on the side if you don't remember it. It says that A implies B, and you also know negation of B. So the conclusion is that it is the negation of A. So here, if I look at this as kind of like a little flow chart just to see how it works out, if I take the first given, P and Q implies S, and then I combine it with the negation of S, well, combining these two using modus tollens, that would then give me the negation of, in parentheses, P and Q, because it's the negation of the if statement, according to MT. Now, again, looking at now what we have and looking at what I'm trying to prove, I definitely do think that we got it, because if you look at number 10, De Morgan's rule, the one we just proved up there, this is exactly the same thing. So here, what I can say is I can use De Morgan's rule. So De Morgan's, oh, that's not how you spell De Morgan's. Let me erase that. So it is going to be De Morgan's rule. We would then get negation of P. We're going to flip the symbol, so then it becomes an OR symbol, and then negation of Q. If you look at De Morgan's rule, it's kind of like the distributive property from algebra. The only thing is that you have to flip the AND and OR symbol vice versa. So there it is. Nonetheless, we have our outline, so now we can go ahead and write the proof. So let's go ahead and see if we can write everything out according to our little flow chart right here. Okay, so here we go. So we have statement, we have reason. So number 1, we say just go ahead and take the given. So we have P and Q implies S, and we also have negation of S. Now at any time, if you take a given, or if you take more than one given at once, you can actually just put them all into one single statement if you want, or one single part if you want. So you don't actually have to write given and then given again. So this is just to kind of save a little bit of time, okay? So those two, now what's going to happen is I'm going to combine them. And the result, according to my chart, is that I am going to get the negation of P and Q. And that right there, according to what we said earlier, is supposed to be MT, mollis tonin, from the last section. Now we can go ahead and use De Morgan's rule to get what we want. So then step number 3 is going to then be negation of P or negation of Q. And the reason for that is, as we said, is De Morgan's rule. And right there, we're done. So it's only 3 steps, which is really, really nice. Okay. All right. So something I need to basically say before we actually move on is that, when it comes to proof writing, you can take 4 steps for a proof. You can take say 10 steps for a proof. But every single time you do it, make sure you ask yourself the question afterward, is it possible to minimize it? Because, as a reader, I definitely would not want to read a proof that is say 20 steps long. I'd rather prefer something that is between the range of say 4 to 10, say what we just talked about. So if you can reduce it, that's great. And if you can't reduce it, so long as it's between 4 to 10 steps, I think we were in a good place then, okay? Nonetheless, let's move on to another example, number 6, which I again stole from kind of like a textbook. Given negation of Q implies negation of P, we have Q implies R, and then we have P. And finally, I want you to use all of that to prove R. So if you want to stop right now and try it on your own, totally fine. But if not, then I'm going to go on then, okay? All right, so again, let's go ahead and think about the strategy. Let's go ahead and write everything out here. In terms of things I can combine together, right? Thinking about kind of like a jigsaw puzzle, what 2 pieces can I put together? I am looking at this guy right here, and I am looking at this guy right here, because you'll notice that they both have P in common. Now, technically, these 2 I can deal with also, but the problem is I don't actually have negation of Q to work off of. Notice what I need to prove, which is R. So then that tells me over here I need Q, but I don't have Q. So then that means we can't really combine those 2 at the moment. But I'm hoping with my first choice, I can do something with that. So let's go ahead and kind of, see what we can get out of it, okay? A lot of this for geometry is, trying to match the right pieces together. It's always basically just like a big jigsaw puzzle to me. You can take a couple of pieces and see if you can match them together and get some new information that might be helpful. That's, just geometry in a nutshell. All right, so here we go. We said take negation of Q implies negation of P, and I was supposed to combine it with P to get a result of that. Now, this right here, it might not be very, very easy to see, but if you look hard enough, this is actually MT because you have the negation of the then statement. Okay, repeat it one more time. You actually have the negation of the then statement. Well, if you're wondering where's the negation of the then statement because this is just P, well, then this is where I need to kind of sneak something in just so you can see it. P, that's the same thing as the negation of P, right? What they call a double negative. When you say something like, say, it is not true that it is not true that it is Tuesday, that's just a say. Again, you're just saying that it is Tuesday. Is that a rule? The answer is yes. Right there, number 6, which we call double negation. So we can definitely use that to kind of sneak it in to help us out. So here's what I'm going to do. I'm going to go ahead and take what we said about P right here, right? And I'm going to go ahead and do the following first. I'm going to take P and I'm going to write it as negation of P because of the double negative, right? So then that way you can see that negation sign. So that means we can now use MT because again, MT on the side, if you remember, I wrote it over here. It requires that you have the negation of the then statement. Once we have that, then that is going to give us the negation of the negation of Q because this right here, negation of Q, that's the then statement and we have the negation of that. Oh, that is rough. That is rough, right? Well, if you're following me so far, then that means you're in a really good shape. Going back to what we did earlier at the very beginning, negation of Q. Well, hey, that is just going to be Q then, using double negative again. And if we have Q, we can then combine that with Q implies R. So then that would then give us the R that we want, and that's going to be MP. All right. All right, so let's see if we can actually put it all together. So then that way we can solve for this. I'm going to go ahead and circle every single one of the reasons that we came up with, and hopefully you can follow all of that and put it together. And from the looks of it, it shouldn't take more than about 5 or 6 steps in this case. Okay, so definitely if you can write this flowchart, draw the flowchart, you should definitely do it, because I always, like, again, as I mentioned in the last time, when I write an essay, I always have to write like a first draft and sometimes a second and a third and a fourth. I was never a good English student. All right, so here we go. Statement and reason, S and R. Okay, so the first we said, hey, let's go ahead and start with P, right? I think that's what was the beginning. So we have the statements P, and that was given. Next, we took P and applied the double negation of it. So then that way we can set it up for using MT. So that right there is the double negative or negation. I can't remember which one it is. Either one, I think it should be okay. Part 3. Now we're going to go ahead and take the statement negation of Q implies negation of P, and that was given. Now, some people sometimes ask, well, since I'm going to use the given eventually, why don't I just put them all together like we did in this problem where I did shove them all into number 1? Well, the problem with that is, as again, the reader, you want to see things as a flow, right? You don't want to use information until it is necessary. So it's actually not good to put them all together and do them all at once. Okay, so back to this. Again, use the given when it's necessary. And here it is, step 4. We're going to now take what we just said and combine it together. Looking at step 2, looking at step 3. Since I have the negation of the then statement, then that means I can use the modus tollens, right? Or you can say MT, or in this one you can say double negation, right? To prove the negation of the if statement. And the negation of the if statement, now keep careful, here's the if statement, it's the negation of Q. So then the negation of the if statement, you have to put a negation in front, okay? So that right there is going to be modus tollens. And again, if you want to write over here, that is from step 2 plus step 3. Okay, putting those two things together. Step 4, as of right now, we are around here in our proof. Okay, did I say step 4? No, I mean step 5. Okay, step 5. We're going to take that double negation and change it back to just the regular statement. So it's just going to be Q. And again, the reason for that is going to be the double negative, okay, or negation. Man, I better keep it consistent, okay? So there's DN. Now we're going to take our last part of the given, right, and combine it together with step 5 then. So I know Q right now. I also know that Q implies R because that was given, right? So notice how, as I said, use the given only when it's when you actually need it. So then that way people can see when you actually are using it versus leaving it alone. Step 7 is going to be just plain old R, and that's going to be modus tollens, okay, or MP for short. All right, so that should do it. Hopefully, if you need to go back and take a look at this video, go for it. It is a little overwhelming, so, it might take some time for it to sink in. But nonetheless, I will see you next time. Thanks for watching.